In this lesson, we will discuss how to find pi groups using the method of repeating variables. In dimensional analysis, there are a few methods for finding the dimensionless groupings of variables called pi groups. The method of repeating variables allows us to find pi groups in a systematic manner, and it is a safe, reliable method for students who are just beginning to learn about dimensional analysis. The method of repeating variables can be broken down into 8 steps. Step 1 involves listing all variables that are involved in the system you are trying to study. The total number of variables is called n. These variables may involve the geometry of the system, the properties of the fluid, the flow conditions, and external forces on the system. The variables should be independent of each other, which means you cannot create one variable from the other variables. For example, if fluid density ρ and gravitational acceleration g are in the list of variables, then the list should not also include the specific weight gamma, since gamma is the product of ρ and g. In a previous video, we discussed a scenario where we wanted to develop a functional relationship for the pressure drop per length of pipe, delta PL, for a pipe that is horizontal and smooth and experiencing steady, incompressible, isothermal, fully developed turbulent flow. We found that delta PL is some function of the flow speed v, pipe diameter d, fluid density ρ, and the fluid's absolute viscosity μ. We have 5 variables, so n is equal to 5. Determining which variables are important in the system you are studying is sometimes difficult. You need a good understanding of the general behavior of fluids and of the physical laws governing the fluid behavior in the system. Great care should be taken in step 1 to ensure that you don't accidentally omit important variables. If you do forget an important variable, you'll end up with an incorrect functional relationship. You also should take great care to only include variables that impact the system significantly. If you include unimportant variables, this will lead to the creation of extra pi groups, and ultimately will cause you to conduct unnecessary experiments, costing you time and money. Fortunately, in most undergraduate fluid mechanics courses, you will be provided with the important variables for the system in the problem statement and only be required to create the pi groups from those variables. Once you have identified the important variables in the system, you can move on to step 2, which is where we determine the number of reference dimensions, k, by expressing each of the variables in terms of their basic dimensions. We will express the basic dimensions of the variables in 2 ways. We use the dimensions of force, length, and time, which we call the FLT dimensional system, and we also use the dimensions of mass, length, and time, which we call the MLT dimensional system. We can convert between the FLT and MLT dimensional systems by noting that force equals mass times acceleration, and acceleration has dimensions of length per time squared. So force F has dimensions of mass m, length L, and time t to the negative 2. We use the equal symbol with a dot on top to indicate equality of dimensions. Rearranging this equation, we see that mass m has dimensions of force F, length L to the negative 1, time t squared. Let's find the dimensions of our 5 variables, delta PL, V, D, ρ, and μ. Delta PL is the pressure drop per length of pipe, and pressure is a force per area. Area has dimensions of length squared. So in the FLT dimensional system, delta PL has dimensions of force per length cubed. We can obtain the dimensions of delta PL in the MLT dimensional system by replacing force with mass, length, time to the negative 2, which gives mass, length to the negative 2, time to the negative 2. Sometimes variables have the same dimensions in both the FLT and MLT systems. The flow speed v has dimensions of length per time in both systems, and pipe diameter d has dimensions of length in both systems. The density ρ is usually expressed as a mass per volume, such as kilograms per cubic meter. So in the MLT system, the dimensions of rho are mass per length cubed. In the FLT system, the dimensions of rho are force, length to the negative 4, time squared. The absolute viscosity mu is often expressed as force time per area, such as Newton seconds per meter squared. So in the FLT system, the dimensions of mu are force, length to the negative 2, time. In the MLT system, the dimensions of mu are mass, length to the negative 1, time to the negative 1. Now we count the number of basic dimensions that appear in the FLT and MLT systems. Notice that FL and T are required to describe the dimensions of the variables in the FLT system. That is, FL and T appear at least once in the FLT column. Similarly, ML and T are required to describe the dimensions of the variables in the MLT system. In order to find the number of reference dimensions K, we compare the number of basic dimensions needed in the FLT and MLT systems and take the smaller of the two numbers. In our case, the number of basic dimensions is the same in both systems. It's 3, and so this is our value of K. Before we move on to the next step, it should be noted that in some situations, the basic dimension of temperature may appear as well. In those situations, we use theta for the basic dimension of temperature, and the FLT and MLT dimensional systems become the FLT theta and MLT theta dimensional systems. However, most situations examined in an undergraduate fluid mechanics course will not contain variables that have temperature as a dimension, so in this video and subsequent videos, we will omit theta as a dimension. Next, we move on to step 3, where we use the Buckingham pi theorem to determine the number of dimensionless pi groups that we need to create. Recall that the Buckingham pi theorem states that the number of pi groups required to study a problem experimentally is equal to the number of variables n minus the number of reference dimensions k. In our situation, n is 5, k is 3, so 5 minus 3 is 2 pi groups. In step 4, we select our repeating variables, which are variables that could potentially appear in all pi groups. The number of repeating variables is equal to the number of reference dimensions k, which is 3 in the current problem. We only consider the independent variables as potential candidates for repeating variables, since the dependent variable, delta PL, should only appear in one of the pi groups, which we will call the dependent pi group. The independent variables that could possibly be selected as repeating variables are v, d, rho, and mu. Here are the variables listed with their basic dimensions in the FLT system. Since the number of reference dimensions k is 3, we need to select 3 out of the 4 variables as our repeating variables. We have some guidelines for selecting a valid set of repeating variables. First, the variables must collectively contain all the basic dimensions that are needed to describe the variables. And recall that in the FLT system, FL and T are needed to describe the dimensions of the variables. Additionally, the set of repeating variables must be dimensionally independent, which means you cannot form a dimensionless quantity by multiplying or dividing the variables. And finally, it will be a little more convenient to select variables that are the simplest dimensionally. A set of variables that meet all of these criteria are v, d, and rho. Notice that FL and T appear in at least one of the variables, and that you cannot multiply or divide these variables in a manner that would result in a dimensionless quantity. Also notice that we have included the variables with the simplest dimensions, diameter d and speed v, in our set of variables. It's important to note that there are other sets of repeating variables that also could have been selected. For example, v, d, and mu would also be okay. For now, we will proceed with using v, d, and rho as our repeating variables, and at the end of this video, we'll discuss what would happen if you chose a different set of repeating variables. Before we move on to step 5, you may be wondering why we use the FLT system instead of the MLT system in step 4. Well, the decision was arbitrary, and using the MLT system also would have been okay. We are now ready to create our first pi group in step 5. This pi group involves our dependent variable, delta PL. We multiply delta PL by the 3 repeating variables raised to an unknown power. Pi1 is equal to delta PL times d to the a, v to the b, rho to the c. The exponents a, b, and c are unknown, and our task is to find the values of a, b, and c that will make pi1 become a dimensionless group. We insert the dimensions of delta PL, d, v, and rho, and we can use either the FLT or MLT system. Here we arbitrarily use the FLT system. Delta PL has dimensions of force per length cubed, d has dimensions of length, v has dimensions of length per time, and rho has dimensions of force length to the negative 4 times squared. We want to find the values of exponents a, b, and c that result in a quantity that has no dimensions, which in the FLT system would be force, length, and time all raised to the power of 0. If we distribute the exponents through each term and combine all the terms with base f, combine all the terms with base L, and combine all the terms with base t, we will have force raised to the power of 1 plus c, length raised to the power of negative 3 plus a plus b minus 4c, and time raised to the power of negative b plus 2c. In order for this equation to be true, the exponents of force, length, and time on the left side of the equation must equal the exponents of force, length, and time on the right side of the equation. So we equate the exponents and develop 3 equations, which are 1 plus c equals 0, negative 3 plus a plus b minus 4c equals 0, and negative b plus 2c equals 0. We have 3 equations and 3 unknowns. Solving for a, b, and c results in a equals 1, b equals negative 2, c equals negative 1. We plug in the values of a, b, and c into the original equation for pi1 and obtain pi1 equals delta PL d over v squared rho. In step 6, we create pi groups using the independent variables that are non-repeating. And in our scenario, we only have one non-repeating independent variable left, which is the absolute viscosity mu. To find the pi group with mu, which we'll call pi2, we multiply mu by the 3 repeating variables raised to an unknown power. Pi2 is equal to mu, d to the a, v to the b, rho to the c. Once again, our task is to find the values of a, b, and c that will make pi2 dimensionless. We insert the FLT dimensions of our variables mu, d, v, and rho. Mu has dimensions of force, length to the negative 2, time. D has dimensions of length, v has dimensions of length per time, and rho has dimensions of force, length to the negative 4, and time squared. The values of exponents a, b, and c must result in a quantity that has no dimensions. If we distribute the exponents through each term and combine all the terms with base f, combine all the terms with base L, and combine all the terms with base t, we have f raised to the power of 1 plus c, L raised to the power of negative 2 plus a plus b minus 4c, and t raised to the power of 1 minus b plus 2c. In order for this equation to be true, the exponents of force, length, and time on the left side of the equation must equal the exponents of force, length, and time on the right side of the equation. So we equate the exponents and develop 3 equations, which are 1 plus c equals 0, negative 2 plus a plus b minus 4c equals 0, and 1 minus b plus 2c equals 0. We now have 3 equations and 3 unknowns, and solving for a, b, and c results in a equals negative 1, b equals negative 1, and c equals negative 1. Plugging the values of a, b, and c into the original equation for pi2, we obtain pi2 equals mu divided by d v rho. Since we only need to find 2 pi groups, we can move on to step 7. If there were more non-repeating independent variables, we would have to repeat this process with each of those variables. When finding pi groups, there is a lot of tedious algebra, and it is very easy to make a simple mistake that would result in an incorrect pi group. So in step 7, we check our work from previous steps by confirming the pi groups are dimensionless in the other dimensional system. Since we use the FLT system to find the pi groups, we will use the MLT system to check that they are indeed dimensionless. This step is technically optional because if you were very careful with the algebra in previous steps, you would simply confirm that your pi groups are dimensionless. But it is considered good practice to perform this step because it is very easy to make a mistake earlier in the problem. We list our pi groups and insert the MLT dimensions of all the variables. Delta PL has dimensions of mass, length to the -2, time to the -2, D has dimensions of length, V has dimensions of length per time, rho has dimensions of mass per length cubed, and mu has dimensions of mass per length per time. You can show that all dimensions do indeed cancel out for both pi groups. If you found that any pi group had dimensions, you would need to go back to previous steps to try to find the error. We have some freedom in our choice of pi groups. We could use the dimensionless groups that were determined in steps 5 and 6, as shown here, or we could use the reciprocal of those dimensionless groups for our pi groups. For example, pi 2 equals rho VD over mu also is a valid pi group. You may notice that this is the Reynolds number. If the reciprocal of a dimensionless group obtained in steps 5 and 6 is a well-known dimensionless quantity, like the Reynolds number, it's customary to write the pi group in its well-known form. In the last step, we write the relationship between all the pi groups. In general, pi 1, which contains a dependent variable, will equal some unknown function phi of pi 2, pi 3, and so on. In our case, we have two pi groups, so pi 1 is equal to some unknown function phi of pi 2. Plugging in the expression for the pi groups, we have delta PL d over v squared rho is equal to some unknown function phi of the Reynolds number. At this point, we would have to conduct experiments to find that function phi. We could create an experiment where we vary the Reynolds number, perhaps by varying the flow speed v, and observing the change in the quantity delta PL d over v squared rho. We then perform a curve fit to the data to find an expression for phi. And finally, we would rearrange the equation to find the expression for our dependent variable delta PL, which is v squared rho over d times the function phi. Back in step 4, we selected v, d, and rho as our repeating variables. But what would happen if we selected a different set of repeating variables? Well, choosing d, v, and rho as our repeating variables resulted in the expression delta PL d over v squared rho equals some function of the Reynolds number. And now let's call this function phi1 instead of phi. Had we chosen another set of variables, say d, v, and mu as our repeating variables, we would end up with different pi groups and a different relationship between those pi groups. With d, v, and mu as the repeating variables, we would find that pi 1 becomes delta PL d squared over v mu is equal to a different function phi 2 of the Reynolds number. We then could conduct experiments to find phi 2 by varying the Reynolds number and observing the change in the quantity delta PL d squared over v mu. And although the functional relationship phi is different in the two cases, when we solve for our dependent variable, delta PL, we would end up with the same overall equation for delta PL. That is, v squared rho over d times phi 1 equals v mu over d squared times phi 2. So while the number of pi groups is the same regardless of our choice of repeating variables, it's n minus k, the pi groups themselves are not unique. But that's okay because we'll wind up with the same equation for the dependent variable in the end, regardless of our choice of repeating variables.